A black hole does not appear as a hole in a literal sense. It behaves like a boundary where the rules of nature begin to change. Imagine standing beside a calm lake when the water bends downward under an unseen influence. The surface remains smooth, yet everything near the center moves toward it with no chance of returning. This simple picture hints at a far stranger reality. A black hole is a region where gravity becomes so strong that not even light can escape. This raises a direct question. What are black holes really? Are they objects, places, processes, or something even more fundamental? We explore them because they sit at the edge of our understanding. They challenge how we think about matter, energy, space, and time. They offer clues about how the universe began, and perhaps how it may end. They show us places where our theories stretch close to their limits. A single black hole can compress material heavier than several suns into a point smaller than a grain of sand. That scale feels almost impossible to imagine. Yet the evidence for their existence grows stronger each year. The question is no longer whether black holes exist. The question is what they truly are. This mystery invites us to look deeper. Black holes entered scientific thought long before we had the tools to observe them. In the late 1700s, a few thinkers proposed the idea of a star so dense that even light could not rise from its surface. The concept was noted, then quietly set aside, because no telescope of that era could test such an extreme prediction. 2 centuries later, Einstein's theory of gravity revived the idea with a clearer mathematical foundation. The modern search began when astronomers noticed stars moving in unusually tight curves. Something massive yet invisible was pulling on them. The motion was as clear as watching a stone tied to a string. You may not see the stone directly, but the path of the string reveals its weight. This indirect evidence became the first solid map pointing toward black holes. Today we search for these objects across the entire sky. Some rest at the centers of galaxies. Some drift quietly on their own. Some exist in pairs that spiral around one another. Each one shapes a region where space behaves differently from the world we know. Why does this matter now? Because black holes influence the growth of galaxies, the birth of stars, and the flow of energy across the universe. They allow us to test physics under extreme conditions. They force us to ask whether our current theories can fully describe nature at its most intense. When we observe black holes, we do not look at the object itself. We look at the environment around it. Gas heats up. Light bends. Time slows. These behaviors create a landscape shaped not by geography, but by gravity itself. To understand how a black hole works, start with a simple image. Imagine a rubber sheet stretched tightly in all directions. Place a heavy ball in the center, and the sheet curves downward. Now roll a smaller ball nearby, and it spirals toward the dip. The sheet is not pulling the ball. The ball is simply following the shape of the surface. This analogy shows how gravity acts not as a force, but as a curve in space. A black hole forms when this curve becomes so steep that it creates a deep funnel with a sharp drop. Nothing can climb back out once it crosses the edge. Physicists call this edge the event horizon. It is not a physical wall. It is the point beyond which escape becomes impossible. In precise terms, a black hole is a region of space-time where the escape velocity exceeds the speed of light. Escape velocity is the speed needed to move away from a gravitational body. For Earth, it is about 11 kilometers per second. It must exceed 300,000 kilometers per second, which is the speed of light. Since nothing can travel faster than light, nothing can escape from inside the horizon. At the center lies what we call a singularity. Here, the analogy with the rubber sheet breaks down. A singularity is not a physical point we can visit. It is a region where our equations lose their meaning. Density becomes extremely high, and our models stop giving clear answers. What does this mechanism create? It shapes the entire environment around the black hole. Matter falling inward heats up. Light bends along curved paths. Time stretches as gravity increases. All these effects combine to form one of the most unusual systems in the universe. Astronomers rely on observations rather than assumptions to study black holes. One of the strongest clues comes from orbital motion. When a visible star moves in a tight circle around an unseen partner, its path reveals the mass of the hidden object. If that mass is several times greater than the Sunday and no light is detected, the simplest explanation is a black hole. The star's orbit becomes a measuring tool. A second clue comes from X-ray emissions. Gas spiraling toward a black hole forms a hot, glowing disk. Temperatures in this region can reach tens of millions of degrees. Only extreme gravity can heat matter to such levels. The brightness and pattern of these X Rays help us calculate how fast the gas is moving and how close it is to the horizon. A third line of evidence comes from gravitational waves. When two black holes merge, they send ripples through space itself. These ripples stretch and compress distances by less than the width of a proton. Sensitive detectors on Earth measure these tiny changes. The signal reveals the masses, the speed of the collision, and the energy released. A fourth clue comes from direct imaging. In 2019, the Event Horizon Telescope produced the first picture of a black hole's shadow. It showed a dark center surrounded by a bright ring of hot gas. The size and shape of this ring matched the predictions of Einstein's equations. This agreement strengthened confidence in our models. A final clue appears in the light coming from matter near the horizon. Its frequency drops as gravity pulls on it, creating what we call gravitational redshift. This shift means that time flows differently near a black hole compared to regions farther away. Each of these observations points toward the same conclusion. Dense, compact, and invisible objects exist across the universe. They behave exactly as general relativity predicts for black holes. The null hypothesis states that our observations do not require a black hole. It assumes that the strange motions, intense radiation, and gravitational signals could come from another kind of dense object. This is our starting point, because science accepts the simplest explanation only after all alternatives fail. The black hole model must earn its place through evidence, not expectation. One alternative is a cluster of neutron stars. Neutron stars are incredibly dense and can produce strong gravitational pull. At first, this seems like a reasonable candidate, but a tight cluster would be unstable. The stars would collide or drift apart in a short cosmic time. Their combined size would also be larger than the compact region we observe. This explanation cannot match the stability or small scale seen in real data. Another idea is a cloud of dark matter. Dark matter does not emit light, so it appears invisible. However, its particles interact very weakly and do not clump into tiny volumes. A cloud dense enough to mimic a black hole would collapse under its own gravity. It would not stay smooth or compact. This model struggles to reproduce the sharp boundaries we detect. A third proposal is a hypothetical object called a gravistar. In theory, a gravistar replaces the interior of a black hole with exotic energy that prevents collapse. It removes the need for a singularity. But there is no observational evidence that such energy states exist. The model also predicts surface effects that should be visible near the boundary. No telescope has detected these features. A fourth alternative is a boson star made of hypothetical particles. These objects could be extremely dense and nearly invisible. But current models suggest they would not match the exact mass, size, and shadow profile seen in real observations. Their behavior would differ in ways we could measure. After testing each option, the simplest explanation remains the standard one. Based on current evidence, the black hole model aligns most closely with every observed feature. Our understanding of black holes is shaped by the limits of our instruments, our models, and the small number of systems we can study in detail. Even the closest black holes are extremely far away, which means the light we observe has traveled for thousands or millions of years. By the time it reaches us, some information is blurred or lost. This distance limits the precision of our measurements. Our telescopes cannot see through the event horizon. They only capture the behavior of matter and light outside it. We cannot directly observe what happens inside, so our conclusions depend on mathematical models. If those models break down at extreme densities, our predictions become uncertain. The resolution of our imaging systems is another limitation. The Event Horizon Telescope produces impressive results, but it still observes only the thick outline around the black hole, not fine details. Small deviations from predictions could exist, but we might not yet have the clarity to detect them. A sharper global network could reveal features that our current system smooths out. Gravitational wave detectors face similar constraints. Their sensitivity is remarkable, but they measure incredibly tiny changes in distance. Noise from earthquakes, weather, and human activity can interfere with the signals. This makes it difficult to capture weak or distant mergers. Our theoretical models also rely on assumptions about matter, energy, and spacetime. If these assumptions are slightly wrong, the predictions may drift away from reality. We may need new physics to describe the core regions of black holes, but we cannot test this directly. What experiments might close these gaps? A larger array of radio telescopes could sharpen images of black hole shadows. Next-generation gravitational wave detectors could observe smaller or more distant mergers. Future space missions may carry instruments far from Earth, reducing noise and opening new measurement possibilities. For now, we work with the best data available and accept that some answers remain beyond our reach. These limits remind us that the deepest mysteries in physics often sit just outside the boundary of what we can measure. If black holes behave exactly as current evidence suggests, their influence reaches far beyond astronomy. They help shape the formation of galaxies by regulating how gas flows and where stars can form. A single massive black hole can control the energy output of an entire galactic center. This means our understanding of cosmic structure depends on understanding these extreme regions. On a scientific level, black holes serve as natural laboratories. They let us test gravity under conditions that no experiment on Earth could recreate. General relativity has passed every test so far, but black holes push it close to breaking. If the theory fails anywhere, it is most likely to fail at the horizon or the singularity. This makes every observation a chance to refine the foundations of physics. There are technological impacts as well. The mathematics developed to study black holes has shaped tools like GPS, which relies on precise time corrections from relativity. Improvements in detectors, imaging networks, and data analysis developed for black hole studies often find use in medicine, communication, and engineering. The search for faint signals trains us to build more sensitive instruments. But there are risks in interpretation. It is easy to imagine black holes as cosmic monsters that swallow everything. In reality, their influence follows the same rules as other massive objects. Only at very close distances does their gravity become extreme. Another risk is assuming that every unexplained signal must involve a black hole. Science needs caution before assigning such labels. Black holes also carry philosophical weight. They challenge our ideas about time, space, and information. If matter falls in and information disappears, our understanding of physics may need revision. If information survives, then the universe may be far more orderly than we assume. Their scale stretches the mind. A stellar black hole can be smaller than a city, yet heavier than several suns. A supermassive black hole can be millions or billions of times heavier than the Sunday, yet its shadow could fit within the orbit of planets. These comparisons remind us how flexible the universe can be. Understanding black holes means understanding some of the deepest rules in nature. The knowledge we gain could reshape cosmology, particle physics, and even technology in ways we cannot yet predict. The mystery of black holes remains one of the most compelling puzzles in physics. The evidence is strong, the models are consistent, yet many details stay hidden behind the horizon. Curiosity drives us forward, but caution keeps our conclusions grounded. The excitement is real, and so is the need for care. We look at these distant objects and see both danger and beauty. They remind us that the universe is shaped by forces far beyond our everyday experience. They also show that nature remains full of unsolved questions waiting for patient minds. What else is hidden in the deep structure of space and time? Could new theories reveal layers of reality we have not yet imagined? If you found this topic intriguing, subscribe to the channel and share your thoughts in the comments.